Anybody else need any? Okay, cool. Oh, you can put this as my other example. Wonderful. Or, I mean, have you guys already figured it out? You guys, you can't talk to each other. I'm just letting you know. That's in the field 0, 1, that's how it works. When there's only two elements, think of it as binary addition. So they're binary numbers, so 1 plus 1 is 0 by 2, so 0.
1 plus 1,
yeah, but we're going to do everything mod 2 is really the right answer. We're doing arithmetic. I didn't want to say that because I don't know how many people took 55 or some discrete math. But so it's, yeah, so if you define 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, then it's a field with everything else exactly as you expect. It turns out. It's actually, but the reason I wanted to show this as an example, just to show you not every field can have it.
1 plus 1 is 0.
Everybody think they have a way to show it? So what's the general idea? That's right. The point is, no matter which, so look, so to prove that, so how do I prove this is not an ordered field? For any order, I have to show no matter what order I pick, it fails, right? Luckily, since there's only two elements, there's only two possible orders. And in fact, I'm about to prove a proposition that says there's actually only one possible order. But let's just assume, and I'm sure you can figure out how the other one goes. Let's say this is our order. Well, what's going to go wrong? Well, as you guys might, as many of you are kind of already noticed, what happens if I add 1 to both sides? Well, according to part 1, this should still be true. But from the properties of our field, this gives us 0 is greater than 1. Do you see that? Because if you, again, when we're working in F2, so the fancy word is you're adding mod 2. If you guys know what that means about, yeah?
How do we know that the only way to make that into a field is to use structure?
How do we know it works? Well, I told you it does. If you want, you can check all 9 axioms. I kind of chose not to yesterday. But
I guess I understand that it works. How do we know that's the only possibility?
Oh, well, because you kind of, what do you have freedom? The point is we prove 0 times 1 has to be 0. We prove, well, 0 times 0 obviously has to be 0. We prove 1 times everything has to be whatever it was, right? So we already know the multiplication can only be one way. The addition, now the question is, well, the only thing that you have any freedom on, this is the additive identity, so 0 plus 0 is 0. 0 plus 1 is 1. So the only freedom you have is 1 plus 1. So what's the other possibility? 1 plus 1 is 1, but that doesn't make any sense because there's only one additive identity. So this is the only field structure. Does that make sense? But okay, so the point is, you can just reverse the inequality just by adding 1 to both sides. And I'm sure you can see if I chose 1 to be less than 0, you get the same phenomenon the other way. Make sense? So this cannot be an ordered field, yeah? Well, okay, so the point is, I mean, I didn't describe it very well yesterday, but the point is the way this field works is everything is what you expect except 1 plus 1 is 0. And this is it's a perfectly good field. If you guys want to try it, you can check, like, prove all 9 axioms. Follow into this. But the point is, since you know 1 plus 1 is 0, adding 1 to this is 0, this is 1. It gives us the other inequality. Because according to this, if I add the same thing to both sides, the inequality should not switch. And that's what I did here. Does that make sense? So it just cannot possibly, so this breaks trichotomy. This can't be an ordered set if it also has 1. So either 1 or the trichotomy rule must break. Does that make sense? So here's a good example. I mean, that's a pretty good example of a field that can't be ordered at all. In fact, it's not an ordered field, but it's also unorderable. There's not a way to order it. Because I'm sure you can imagine I can put an order on R that makes it not an ordered field. That doesn't mean there isn't an order. Does that make sense? So you are asked on your homework on one of the problems says prove C is there's no order on C that makes it an ordered field. So this is not like the easiest question, but the point is don't just show look there's an order that doesn't work. Because I could go to R or Q in order that doesn't work. Okay? And technically I shouldn't keep saying R, but I keep saying it because I know you guys know it. I technically haven't told you it exists yet. I'm telling you that today eventually. Whatever. These pedagogical things, whatever. This is mathematicians from the 60s like yelling at me from far away because like you haven't defined R, how can you talk about R? Okay, so are we happy with this? So let's prove a few properties about ordered fields, just so we can show some nice things, and I can make a couple comments about stuff you're going to be doing at home. So proposition maybe. Let F be an ordered field. With order less than. Oh yeah, so just, I'm sure you guys all figured this out, but you can always, if X is less than Y, feel free to write Y is greater than X. I didn't say that explicitly when we talked about ordered sets, but we allow that just because it makes writing things later much easier, so you have both directions are possible. But you guys know that. I didn't mention it specifically. So if I ever write greater than, because I'm about to write greater than, I just mean the other way technically, if you want to be really technical about it. So the following things are true. Let X, Y, and Z be an F. Then we have if X is greater than 0, or otherwise X 0 is less than X, right? Oh, I'm sure you get it. I'm going to stop. Then minus X is less than 0. If X is greater than 0, and Y is less than Z, XY is less than X. This is what I put originally because of, well, whatever, it doesn't matter. I think you can take two of these and still define an ordered field with that instead, but I'm using Rudin's definition. If X is less than 0, Y is less than Z, then Y is, which should I do? Okay, go greater than XZ. If X is not 0, X squared is positive. So just, thus 1 must be greater than 0. Yeah? If 1 times 1 itself is 1. So 1 is always a square in every field. So the only one way to check really quickly is this in order is 1 positive. Okay? And that's why I was saying there's only one possible order here. The other order wouldn't even work because I'm about to prove every ordered field has this property. Okay, cool. If 0 is less than X less than Y, oh yeah, this one's the fun one. Then 0 is less than 1 over Y is less than 1 over X.